I'm not connected the tablet. Yeah. So last time we saw the complex exponentials were. So we made the point that this complex exponential. So when you take e lambda of x, e lambda of x is e to the I lambda x. That is a homomorphism from the additive group of real numbers into this circle group T, which I'll always denote T. Okay, so the circle, so because just exponential has this property. Now it's also, if you take lambda to be an integer, then it's also homomorphism from the additive group 0 to 2 pi modulo 2 pi. So you take addition modulo 2 pi of this, then it is a homomorphism for only integer lambda, that is ek. For k, both positive and negative integers give homomorphisms. So, and I left you to check that these are all the continuous homomorphisms in both cases. Okay, so this is, as I said, it's a familiar problem. Fx plus y is fxf plus fxfy. Does that mean f is exponential? Without any conditions on f, that is not true. It is exponential when you restrict to rationals, but to go beyond that, you need some mild condition of regularity on f. Like continuity is definitely enough. Measurability, continuity, something is needed. Okay, so this is the moral. So the question that we now start with is, okay, I haven't answered this, why homomorphisms into the circle group. Maybe we'll say something about that later. But the question is, for a general group, is this a meaningful way to get a basis? So what is it that, okay, still don't know. Does it give some particular nice functions taking homomorphisms into the circle group? And what will that give us? Okay, so that is the question we want to talk about. Okay, so let's start with the simplest groups, namely the cyclic groups. Okay, so that's where I will start today's lecture. So just 1 second. Okay, so let's start with the simplest group, namely the cyclic group. So Z mod n. Okay, so I will, since I'll write it too many times, I'll just be lazy and write it as Zn. Okay, so Z mod n is Z sub n is what I will write. So it is notation wise, we will use 0, 1 up to, I will always write it like this with addition modulo n. Addition modulo n. Okay, so that's a group. It's a cyclic group. I mean, also all finite cyclic groups are like this. And so this is the one. So question is, what are, so the similar to the question that we asked here. So what we want to do is, what are the homomorphisms? I mean, here we said these E lambdas and EK, so the only continuous homomorphisms from the corresponding group R or T into the circle group, right? So we want to ask the same question, but here continuity is trivial. It's a finite group. There is no question of continuity. If you want, there is a discrete topology on this, and every function is continuous. So only question is, what are the homomorphisms? So the question, so I will introduce a name here. What are the characters of this group? Okay, so here let me define character of G is means. So let me just write continuous in the bracket. From G into the circle group. So T is, you may remember, it is with multiplication, right? So it's a multiplicative group. So character of G means continuous. Okay, continuous may or may not make sense. So I have, so for a general group, what is continuous, right? Okay. So don't worry about that point now. For a while, we are going to stay with finite groups. But when we come to groups which have a topology, I mean, even finite groups have a topology, namely discrete topology. But in general, the correct notion is what is called a topological group with a topology. But we don't need all those. I may mention it later, but we will not need to worry about it much. So it is really specific examples that matter to us. Particularly, we will be concerned with finite groups. So our interest is in finite, and as we will soon see, it will be finite abelian groups, particularly Zn. And then we have the circle group itself, which is 0 to pi t, which is 0 to pi with addition mod n mod 2 pi. That is the other one, and r. And powers of it. We may care about td and rd. Okay, so these are actually the examples which really we are interested in. So people who are not there's no group theory that we will use, but people who are not really very comfortable may really concentrate on the examples. That is what is important. But to some extent, we can do things in general, and we will do that. So what are the characters of Zn? That is the question. Now, the answer is very simple, actually. So this is a cyclic group. So a homomorphism, we want a homomorphism from Zn into the circle group, right? So this is the circle group, and here is 1. So where can you send this 1? Okay, so let F be since it's a cyclic group, all we need to decide is F of 1, because then F of k will be F of 1 to the power k, because k for k between 0 and n minus 1, because k can be written as 1 plus 1 plus 1 k times. The homomorphism says that that will be F of 1 times F of 1 k times. So that is what it is. Now, so that is, so what is F of 1? But you can also see what happens if you add n 1 times. So you don't have to restrict to k n minus 1. So 1 plus 1 n times is 0. In this group. Hence, F of 1 to the power n must be equal to F of 0. F of 0 is anyway going to be 1. I mean, you can see it here. All homomorphisms anyway have to take identity to identity. So F of 0 has to be 1. So what this shows is that F of 1 is a nth root of 1. So it is one of the n roots of 1. So what are the n roots of 1? So, well, it belongs to e to the 2 pi I k over n. K can be anything from 0 to n minus 1. Right, so e to the 2 pi I by n, e to the 2 pi I, 4 pi I into by n, etc. and so on up to some e to the 2 pi I n minus 1 by n. These are equispaced points, and this itself is actually e to the 1 itself is a root, of course, e to the 2 pi I 0 by n. So these are all the nth roots of 1, and f of 1 has to be one of them. But in fact, we get one for each of them actually. So that is also clear. So for each k, let chi k of J be defined by, so let chi k be the, let chi k be the that homomorphism which has that property that it maps 0 to chi k be the homomorphism that takes 1 to this one. So let's, according to our earlier notation, this is e2 pi k by n, right? This is what this is actually. So, well, okay. Did I write like this? What did I write? E2 pi k by n of 1 actually. This will be e2 pi k of by n. Okay. Anyway, never mind. Let's not worry about that. So chi k be the homomorphism that takes to 1 to e to the, actually so that is chi k of j will be e to the 2 pi I that raised to the power j for j in the group, right? So this is a homomorphism. That it is a homomorphism is clear. It's a homomorphism is clear, right? So this gives you all the homomorphisms of Zn, because we argued that any homomorphism f of 1 must map to some root of unity. And for each root of unity, there is a unique homomorphism, namely I denoted it chi k. Actually, the extra notation was not necessary. I could have called this E2 pi k by n of j. According to my earlier notation, E lambda of x is e to the I lambda x. So it is actually e2 pi k by n applied to the number j. So I can call it e2 pi k by n. Okay, so that's also fine, but okay, I just denoted chi k. Chi is the standard symbol we will use for characters. So this is all the homomorphisms of Zi. Okay, so well, good. So what about it? So here is the single most important point, which I actually also said last time. So what is the most important point? So we have found all the homomorphisms. What about it? You look at, okay, so let's introduce some notation which is not which can be avoided here, but there's no need to avoid. So what is the notation? So let's write L2 of G denote the set of all functions from G to complex numbers. Okay, so here for me at the moment it is finite. Okay, so G is a finite set like Zn. So L2 of G is all the functions from G to C, which you can also identify with Cn if the size of G is n, right? Because, well, how do you identify? You identify a function with the vector. Well, okay, so in this case, the vector f of you order the elements of G in some way, G1 up to Gn, sorry, G capital N, and then you call that. So it's just another way of writing Cn, but it's a, and this looks like a heavy notation if you have never seen, but L2 of G is really, for those who understand, it is the counting measure on this finite set, and L2 is the L2. All any function. Okay, so this is a vector space. So it's a vector space, but it also carries an inner product. With inner product, how is the inner product of two functions defined? Okay, maybe I should have. Yeah, so I called the elements of the group as G's. I mean, let me call them x1, x2, xn. The ordering is not important. If you want to identify it with Cn, then you need an ordering, but I'm not going to use the ordering at all. This is just to say that if you want, you can think of it as just Cn. Okay, for me, the ordering will not be important. The inner, so if you take this ordering, what is the inner product in Cn? You take the corresponding coordinates, multiply with the second one conjugated, and then add them up, right? So the same one. So irrespective of the order, this will give me sum over x in the set fx gx conjugate. So this is the inner product. Okay, so L2 of G is a complex vector space. It's a complex vector space with this inner product, and the norm, corresponding norm, will be denoted. Sometimes we may write 2, or if we want to be very clear, we will write like this, is just sum of squares, absolute squares of the values of f. Okay, so this is the vector space we'll be working with all through. Every function, so functions on the group can be thought of as vectors also if you want. Anyway, with this notation, so here is the important, this is with this notation, now we come to the most important fact. Okay, before that, by the way, this is of course an n-dimensional vector space. It's an n-dimensional complex vector space with this inner product. So what is the most important fact here? So we talked about the, so actually this was in general. So I am now returning to this Zn situation. Okay. So these characters chi n minus 1 are orthogonal in this L2 of Zn. Okay, so what does that mean? In fact, what is it that I want to write? So if you take chi k inner product chi L, let's compute that in L2 of Zn. When needed, I mean, so I will usually not write all this under this, but let's for the moment write it so that is chi k inner product chi L. Okay, so k and L. So what is that inner product? By definition, here it is just the sum over. Here we are doing over Zn, j equals 0 to n minus 1, chi k of x, chi k of j, and chi L of j conjugate. But that is just, this is e to the 2 pi I kj over n. And then if this is, since we are conjugating, it will become e to the minus 2 pi I k L, lj over n. So which is, well, it is e to the 2 pi I j over n into k minus L. You are summing over j equals 0 to n minus 1. So what do you get when you do this? The claim is that if k is equal to L, Then it says if k equal to L, this is 0. So all of these are 1. So you get n if k is equal to L, right? Because each of these is 1. What if k is not equal to L? I claim that it is 0. So do you see that if k is not equal to L, this is 0. Why so? So suppose k minus L is 1. Then you are summing over all the nth roots of 1. So you get 0. This we discussed last time, right? I said most important identity in analysis and all that hype. So this thing that the sum of these roots of unity is 0. So that's all. So if k minus L is 1, then you get sum over. What if k minus L is something else? What do you get here? You don't get necessarily sum over all the nth roots of unity, but you will get over some mth roots of unity. For example, I mean, so what can happen is, so if you think of, so n is 4, then there are 4 roots of unity, minus 1 and minus I. So this is, if I take here k minus L is 2, then I am only summing over this and this. Actually, I mean, each of those will come 2 times because you are starting with 2 by 4. So you get actually, yeah, you just get, you don't necessarily get all the roots of unity, but you will get some mth roots of unity because this is because the sum is over. For some m. If k minus L has no common factor with n, then you will sum over all the nth roots of unity. Otherwise, you will sum over only the some subset of the roots of unity, but not any mth roots for some. So that's why you get this. So this is wonderful because this gives you an orthogonal set in L2 of Zn, and we can, and since there are n of them, so the basis, the dimension of this vector space is n, and we have found n of them. So you get an actually a basis. So as a consequence, but to make it an orthonormal basis, I don't want the norms to be n but 1. So if I take 1 by square root n chi k, is an orthonormal basis. Of L2 of G. Okay. So, by the way, I said earlier that later I will take stock of how much people who stay actually know. So, if you know Hilbert spaces, L2 spaces, and so on, and depending on that, we will decide. Okay. But I will certainly assume that everyone knows linear algebra and finite dimensional inner product spaces and all that. So, orthonormal basis is something that you will be familiar with. I'll have to assume all that. Okay, so these things form an orthonormal basis for L2 of G. So it's actually a very nice ortho. Actually, you can produce Zn, L2 of Zn. See, there are other orthonormal bases of L2 of Zn. The standard one, if you identify it as Cn, what is the standard orthonormal basis you will take in Cn? The one where you take coordinate vectors, 1 in one place and 0 in the rest, right? So that would be the function. So I mean, a different orthonormal basis would be, if you think of it in this way as Cn, the more natural one is, we can call it delta k. So let delta k from, if you take Zn to C, be defined by delta k of j is 1 if j is equal to k and 0 otherwise. So then this is also a delta 0 to delta n minus 1 is also an orthonormal basis. This is the standard orthonormal basis of coordinate vectors, but these characters are much nicer. They don't have any nice properties as group. When you think of Zn as a group, these delta functions have nothing. They're no nothing nice. But these characters are nice. They are actually very. So this is actually a much better basis. I mean more interesting basis. It will be very useful. Okay. So this is the point. So once you have an orthonormal basis, what can you do? You can expand anything in that. So here we come to the definition. It's not really yeah. So now we come to, because it's an orthonormal basis, therefore you take any f in the vector space, you can write it in terms of the orthonormal basis, right? How do you write it in terms of the orthonormal basis? You write it over sum over k equals 0 to n minus 1. That's the number of, I mean, these bases. So you can write it as a linear combination of this. F will be a linear combination of this chi k over square root n, and what will you have here? The inner product, so the coefficients, because it's an orthonormal basis, the coefficients will be the inner product. Or rather, now I will give a name, that is a definition. So let's call it, we can write it with coefficients, which we will call f hat of k. Okay, where f hat of k is nothing but the inner product of f with that orthonormal basis element, namely chi k over square root n. Okay, so this for for k in 0 to n minus 1. Okay, you can write it out if you want. You can just it may be instructive to just write this out. K equals 0 to n minus 1. So what this means is that f at any element j is f hat of k times chi k of j. So I have taken the 1 by root n outside. Chi k of j is e to the 2 pi I jk by n. Okay. Whereas f hat of k, you can also write this out if you want. So that is actually 1 by square root n, and this is, what is that? That inner product is sum over j equals 0 to n minus 1, the group elements of f of j times the conjugate here, right? Yeah, the conjugate will be e to the minus 2 pi I jk by n. So this is the definition of f hat of k, and f of f can be recovered from f hat in this way. Okay, so this function f hat is also a function on. Sorry, again here this was for f in all in Zn. So f hat is a function from 0 1 up to n minus 1 to complex numbers. Okay, so from f, actually that's also like Zn, but for the moment let's not confuse it. I mean, it may get confusing if I say that it is Zn. It's not exactly Zn. It is okay, it's indexed by the same things as Zn, but for the moment let's keep it separate. So from f, so the yeah, so f hat is called the, so when we say it in more generality, things will be clear. So the definition is f hat is called the, so sometimes we say the word discrete, but anyway I will drop that because we will be all the time talking about these things. So discrete Fourier transform of f. So from a function on 0 1 to n minus 1, yeah, so if you forget all this group business, So you have a function on 0, 1 to n minus 1, and you get another function on 0, 1 to n minus 1. Okay, so if that you can for the moment view it that way. Okay, so from one function of 0, 1 to n minus 1, so it's a f going to f hat is a map from L2 of this set to itself. Is it okay? So any questions, comments here? As I said in another class, so please feel free to interrupt at any time. If things are not clear, you can ask me. Okay, so you just unmute yourself and ask questions. Don't ask anything in chat. I'm unlikely to see it when I'm on the other OneNote. If you write anything in chat, I will not be able to see. Okay, so we get one. So what? So some very basic observations about this. Let's make some basic observations about this. I'll give examples. Maybe yeah, we'll give examples. But first, let's do some very simple observations, all of which are more or less direct. So if I take so f is like this, right? So it is expanded in an orthonormal basis. So then the norm square can be written in terms of the sum of squares of the coefficients. You know this, right? So norm f square, which is, by the way, just f of j square, is the same as f hat of k squared, which you can write as norm f hat square in L2 of this. Okay, norm f hat square in that L2 space, right? So the f to f hat is preserves the norm. It's immediate. From any time you expand anything in an orthonormal basis, the sum of squares of the coefficients is the same as the norm square of the original function. More generally, in fact, you can take inner product of two things in L2 of this same thing, L2Zn. So this is by definition fx gx conjugate. So inner product also can be computed using the orthonormal basis, right? I mean, this will be just the sum of f hat of k g hat of k conjugate. Okay, so okay, if you do not recall for whatever reason, if you confuse, it's just you just do it. Actually, you take f inner product g, then you get the sum over all k and l, f hat of k, g hat of k bar, chi k over root n, inner product chi l over root n. I mean, you just do the inner product and use bilinearity of the inner product. You get this inner product with chi l over root n, but that's 0 unless k equals l. So you just get f hat of k, g hat of k bar, which is the inner product of f hat and g hat as seen in L2 of this space. So it's actually this transformation which takes f to f hat is a unitary transformation. It preserves the inner product. So what one can say, this is called, so we will see these things in more generality, but this is called Plancherel relation. One of the most important things which will be very useful, Plancherel relation. So one way of saying is that f going to f hat is a unitary transformation. Okay, because it preserves inner products and consequently also the norms. Okay. Another observation. So this is the Plancherel relation. Another observation you see. So f. How do I get f from f hat? F of j is 1 by root n summation f hat of k e to the 2 pi I j k by n. And what is f hat? F hat of k is 1 by root n sum of f of j e to the minus 2 pi I j k by n. It looks more or less the same, right? The way you get f from f hat and the way you get f hat from f. Almost identical except for the negative sign here. Okay, so that is another small observation that we will see. So it's almost like its own inverse. So the way you get f from f hat is the same, almost the same as you get f hat from f. So to make it, it's not exactly the same because this has a negative. So let's define another operation. So let instead of hat, this is an inverted hat. It is pronounced check. Okay, check. Like in chess. So G check of J, G check of K is defined as 1 by square root n sum over J equals 0 to n minus 1. We will define it exactly like we define the hat. Hat of K is like this, but G check will be defined with without the negative sign. Okay, that's how we define it. So the hat has a negative sign, whereas the check does not have a negative sign. That's the only difference. Then it's almost the same as hat, looks more or less the same. For example, if g is an even function, meaning g of minus j is g of j. Well, minus j should be interpreted, everything is modulo n. But suppose g has that symmetry, g of minus j is g of j, then check and hat are going to be the same for that sort of function. But anyway, it looks very similar. So then what we can say from these two formulas is, how do you get f hat is this? How do you get f? F is the, then, okay, so then f hat, if I apply check to that, I get back f. Okay, so imagine f hat is this. Now if I apply, what is this? How do I get f from f hat? That is precisely my definition of check, right? F hat check is going to be f. So this is called Fourier inversion formula. I mean, it looks like names for some seemingly trivial points, but these are useful things. So of course, being a unitary transformation, there is going to be an inverse. So if you can go from f to f hat, you can go back from f hat to f. There is going to be an inverse abstractly. But a point to note here is that the inverse is more or less the same transformation. Okay, slight difference. So that is this check instead of the hat. Okay, so what would you get if you get hat itself? If you applied, just to observe, note, if you apply hat itself twice, you don't get back f. What will you get if hat of j will be actually f of minus j? You don't get back the function, you get back the function flipped over, because if you apply f hat, then, well, what is f hat of j? This is summation f hat of k e to the 2 pi I j k by n. K equals 0 to n minus 1 with a 1 by square root n outside. It is same as f hat will be this. What is that? Sorry, f hat will have a negative. Sorry. F hat will have a negative here. Now this is the same as, I can absorb that minus into j. So that will be, if you look at this formula, it is f of minus j. So applying hat twice will not give you back the function. Well, so it will give you f flipped. Hence, if you want to get back f, if you don't want this check business, you can apply it 4 times. Because doing it twice will flip it over, and doing it twice more will flip it again, and you will get back f. So Fourier transform in this way, if you think of it as functions, mapping functions from 0 to n minus 1 to itself, it's an operation which you repeat 4 times, you get back the function. Okay, so it's a, is that okay? Any questions here? I mean, nothing is complicated, but if you have never seen, I mean, some things may go fast. So that's why if you have questions, do ask. So this is a linear transformation, right? We in fact said that it's a unitary transformation. So there's a matrix which maps f to f hat. I'm going to write that matrix soon. So what will this tell you? For example, about that matrix, if you apply it 4 times, you get back the, so 4 times the matrix to the power 4 will be identity. So what can you say about that matrix? Anything about that matrix? Yes.
Its eigenvalues
Will be what?
1 minus 1
I minus I. Yeah, exactly. So since the 4th power of a matrix is going to be 1, the eigenvalue to the power 4 has to be 1. So all the eigenvalues of this transformation are actually one of these 4 fourth roots of unity. Okay, so that's a point. So this is the Fourier inversion formula. Okay, what else do I want to say? Maybe I should give an example. Okay, so let's compute some example Fourier transform. So any questions, by the way?
Did we implicitly use Cayley-Hamilton here? Because a matrix equation, you have turned it into a eigenvalue equation, a power 4 equal to.
No, I didn't use any Cayley-Hamilton or anything. I mean, so where is the, no, I just said that if you apply it 4 times, you get back the same function. So
but that is a matrix equation.
Well, this is a linear transformation applied 4 times. The same as the matrix multiplied 4 times. I mean, I just said that, well, you can talk of eigenvalues of linear transformations. We can go back between linear transformations and matrices. So to a linear transformation, we can associate matrix, provided you identify some basis. Okay, whatever basis you identify, and composition of linear transformation corresponds to products of matrices. So this is a basic fact. So composing the linear transformation 4 times is same as multiplying the matrix 4 times. So the matrix is not uniquely defined unless we identify a basis for this space.
Okay.
So we can take the coordinate basis, then we get some matrix. So that matrix to the power 4, it doesn't matter which matrix you pick, it will be to the power 4 will give you identity matrix.
Okay.
Yeah, but do we need, sorry, do we even need to talk about matrices? As in, we have a linear map whose power 4 is identity. So
yeah, no, it is fine. It's you don't need to talk about matrices. You can say eigenvalue of the linear transformation. That's fine.
Okay.
It's, I mean, yeah. So the eigenvalues of the linear transformation and of the associated matrices are all the same. I mean, by definition, more or less. Okay, so let me compute. Any other questions? Let's start with a trivial example. So let f be delta 0. That means fx is 1, fx equal to 0, and 0 if x not equal to 0. All these are functions from Zn to complex numbers. Okay, so this is 1 for 0, and so what is its Fourier transform? F hat of k will be 1 by square root n. By definition, it's the inner product between f and chi k, but f is 0 everywhere, right? Except at 1. So it will be actually except at 0. So it will be chi k of 0 by square root of n. And what is that? Chi k of 0 is actually 1, right? What is chi k of 0? Chi k of j is, you remember, chi k of j is e to the 2 pi I jk by n. Where did I introduce it? chi k of j is e to the 2 pi I jk by n. So when you put j equal to 0, you get 1. So it is actually 1 by square root of n. So as a function, f hat is a constant. So f hat is the constant function 1 by square root of n. So it's the constant function 1. Well, by root n. So next, let's take f to be the constant function 1. Then, so this is constant. So then what is f hat? One by root n f inner product chi k, which is f of j chi k of j bar, which is like, oops, what happened? Hello. Can you hear me? I mean, I lost connection for a moment. Am I audible?
Yeah.
Yes, sir.
Okay. And sharing is not interrupted, right? Can you see?
Yes,
Yeah.
sir. Yes.
No.
Now I.
Now it is not very clear.
Now we can see a blank screen.
Hello.
We can hear you, but
So actually, I was again. Yeah, I don't know. I was again kicked out and I came back. So just hold on. Let me open the door here. Right. So yeah. So it says bad network quality. So is the OneNote shared? I mean, can you see it?
No, so you'll have to reshare the screen.
Okay. I see. Okay. So there is this other problem. Hold on. Okay. I shared it again. Recording, I hope, is continuing. Let me just check that. Okay, so the recording seems to be uninterrupted, and now I have shared the screen. Can you see it now?
yes, sir.
Okay. Okay, so let's come back. Let me repeat again from here. So we computed for the delta function. We compute now for the constant function 1. F hat of k is 1 over n f of j chi k of j bar summed over j equals 0 to n minus 1, which is f is 1. So it is just e to the 2 pi I j k over n summed over j equals 0 to n minus 1, and we have seen. So this is 0 if k not equal to 0, and if k because then you sum over some roots of unity, right? And if k equal to 0, then all these are 1. So you get so n times you get, and then you get square root of n. So in other words, f hat is square root n times delta 0. So you could have got it from Fourier inversion formula from the previous example, but I just did it. Okay. So let's do one more example, maybe. So one thing you see that when f is the delta function, f hat is the constant function, and f is constant function, f hat is the delta function. Well, with some scaling. So this is actually some model that we will see here, but let me just go a little more. Let me do one more example. So by the way, what is the time? Okay, I still have time. Suppose n is p times q. I don't mean they are primes or anything like that. N is product of two numbers, and let f of j be 1 if j is 0 mod p and 0 otherwise. So if I plot this function, so here is 0, 1 up to p, and then 2p and so on up to n. So this is a function which is like a bunch of spikes. So if you want to introduce graphically, it is 1 at 0, p, 2p, and so on, and it is 0 elsewhere. Okay, so that's the kind of function this is. And so this goes up to -1 here. So it's a bunch of spikes. What is its Fourier transform? J equals 0 to n minus 1. Okay, f of j, chi k of j bar. Okay, I will stop writing this again and again. So this is the definition of f hat of k, but now we only f is 0 unless you are 0 mod p. So what do I get? I get, so let's write L equals 0 to, how many are there? When you have multiples of p, right? So you get chi k of L times p. L equals 0 to q minus 1. So this is what we get because the multiples are 0, p, 2p up to L minus 1 times, q minus 1 times p. So that's what we get. Okay, and that is, what is that? What that is 1 by square root n e to the 2 pi I. Okay, I get a negative here. E to the, oh, sorry, earlier I forgot here a negative, right? Which didn't matter actually there, but it may slightly matter here. 2 pi I k LP over n. L equals 0 to q minus 1. And what is that? 1 by square root n. So this p by n is actually, this becomes q, right? N is p times q. So I'm getting e to the 2 pi I k L by q. So what will I get? I am summing over L equals 0 to q minus 1. So what will I get? It's again the same problem again and again. So we have seen this before. So what will you get? Now you will get, so if k is 0 mod q, if k is 0 mod q, that is if k is 0, then all of these are 1. So I'll get q. I'll get, so I'll get q. I'll get q over square root n, right? Because am I right about that? Yeah. So if k is 0 mod q, then I'll get q over square root n, it seems. And if k is not 0 mod q, then I get 0. This is actually the same issue as before, except that now this k can go from 0 to n minus 1. So it is not, if from 0 to q minus 1, there is only one place where you get a non-zero term, namely k equal to 0. But then when you go q plus 1 and so on to 2q again, you will get q plus 1 and so on. It's just repetitive, so it's just periodic. So you get at q2, at 0, q, 2q and so on, you get all the summands are 1, so you get q by root 10, and at others it is 0. It's exactly the same fact I was using before. Now you see, it's what is f hat? F hat is very much like f. F hat, this is f. What does f hat look like? Well, it is not, it's a constant.
Is it k, this mod q or mod p?
No, this is mod q because you have 2kl over q.
I see. Okay, thanks.
So the p cancelled here. What I was left with was q. Therefore, I'm summing over so basically I'm summing over roots of q. I mean, let's say k is 1. If k is 1, you're summing over all the qth roots of 1. So you will get 0.
Okay. Fine. Thanks.
Yeah. So at multiples of q, this will cancel and you will just get 1 so many times. So you'll get q times 1 and then by root n. So you get this. So this looks like this. It is a bunch of spikes except that it is at q, 2q and so on. Okay, so it's a very similar thing to, this is what f hat looks like. F is spikes at multiples of p, f hat is spikes at multiples of q. So there is something funny about this. So if n is like, so it's a generalization of this. By the way, both of these you can take as a special case of this because I can write it as n as 1 times n. And these are actually special cases of that. But the thing is, so think of fixed n. So let's say n is 24. So I can write it as 2 into 12. P is here, Q is here. So now, and or let's write it as 12 times 2. So, or you can write it as multiple in many ways. So let's just write a couple of them. 8 into 3 or 6 into 4 or 3 into 8 or 2 into 12. So there are many ways to write it. Of course, you can also write it as 1 into 24. So here when P is 12, what does this mean? F is supported on exactly 2 points, right? So n is 24. There are only 2 points where F has the support, namely f of 0 and f of 12 are non-zero. Everything else is 0. Then F hat will be supported on multiples of 2. That means there will be 12 points where F hat is non-zero. Okay. So if the support of F is small, then the support of F hat is large, and conversely. So if F hat is supported on a small set, like F hat is 0 everywhere except 1 point, meaning then F will be supported on, will be a constant. So that's what happens here. So this is actually a theme that will come again and again called uncertainty principle. So we will come to it. It's an important fact about Fourier transform, uncertainty principle. So this is saying that if both F and F hat cannot have small support, well, we have not proved any such thing. We have seen in this specific type of example that if I make F to have small support, F hat will have large support. Okay. So we will come to this principle. We will prove various versions of it in discrete, in continuous, and everywhere. Okay. Okay. So that's about the Fourier analysis on Zn. So main question that next is, can we do it on general groups? So the next question that we will take up next lecture is.
It's 1 o'clock.
Okay, I will stop by stating this. Can we do this? All this on general. Let's even say finite. Okay, can we do this on general finite groups? Actually, it will turn out the answer is no. So for those who want to just try some exercise beforehand, I will do this next time. But if you want to try, you look at test 3, which is the permutation group on. And show that you can only find 2 characters here, or even in general on Sn. See, to get a full basis, we need 6 characters, but there are only 2 characters. Okay, anyone who wants to try as exercise is welcome to, but I will stop here. Okay, so